reminding me. I'm going to start recording now. Yeah, if I ever forget to start recording up there, please let me know. Okay, so we're keeping it fairly general now. We're talking about lots of different ways that you can set up a computer to operate. We're talking about the architecture of a computer, how it is put together. And when we talk about an instruction set architecture, an instruction set, again, is the list of instructions that a particular computer has been designed to execute. Okay, and although they are similar from computer to computer, there are slight differences. We're going to be concentrating on the ARM processor in this course. There are lots of other different types of processors. They have their own instruction sets, but every computer instruction set has an instruction that, for instance, will add two numbers together or subtract two numbers. But the way they do it, in particular, the addressing methods can sometimes vary. Sometimes it's just the syntax, the way you write it, okay, that varies from computer to computer. So another important classification that some of you might have heard of when we talk about different computers, we talk about RISC versus CISC, okay? And RISC is what we call reduced instruction set computers, okay? And so this is a broad range of computers that have certain attributes, and perhaps the most important is that the instructions themselves have fixed sizes. That means when we talk about the size of an instruction, we're talking about the number of bits that are required to encode that instruction in machine language. Okay, so in RISC computers, the instructions have a fixed size, 32 bits, or maybe 64 bits, okay? Every instruction takes that number of bits. As to opposed to a complex instruction set computer down here, where we can have specialized instruction sizes. Some instructions might require one word to be encoded, like 32 bits. Some might require two words to be encoded, 64 bits, okay? In CISC machines, every instruction can be slightly different or have different lengths. In a RISC instruction set computer, we have what we call a load store architecture, which means, you know, you have the CPU, you have a memory unit that is physically separate from the CPU. It's in the same computer, but physically separated on different chips, okay? And whenever the CPU needs a number, it has to go to memory and load that number into one of the registers in the CPU, okay? The CPU, we constantly are getting loading from the CPU and storing back to the CPU. That's what we call a load store architecture, okay? And that means that the instructions, we have in an instruction set for a RISC machine, we've got certain instructions. All they do is go get a number from memory and load it into a register in a CPU. We have other instructions. All they do is store a number from a register in the CPU back to memory. And then we have yet other instructions that actually crunch the numbers inside the CPU. Okay, so the instructions are separate. In a complex instruction set computer, the instructions are more complex, and therefore it's possible that a single instruction can go to memory, get a number, and add it to another number that's already in the CPU, or even add two numbers from memory. Okay, but in a RISC computer, you always have to write an instruction to go get the number from memory first. We call that load. Go and get the second number from memory, call that load. Add the two numbers together in the CPU and then store the result back. Okay, and we're going to look at some examples as we get into the next set of lecture notes. Now, there's a bunch of other differences here that I'm not going to really spend much time talking about. These are simpler instructions. Every instruction does less, therefore you typically need more instructions. These are more complex instructions. Every instruction can do more, okay, so you typically need fewer instructions to accomplish a certain task. But that requires a lot more hardware, okay, in order to do these complex instructions. The RISC it's very, very simple because the instructions are simple. It's simple to implement the hardware that executes those instructions. Okay, so that's all we need to talk about. The ARM is basically a RISC processor. It has some attributes of CISC, So you know it's not black and white, that it's either RISC or CISC. Some are kind of a mix, and the ARM is that, although it's primarily a RISC architecture. Yeah.
So what would be some applications of going, for example, with RISC over CISC?
Like where would you use one over the other?
Yeah, like if I was to use, say, for example, with my Intel computer versus like a supercomputer or something like that, would there be a preference of one over the other?
Probably in terms of the hardware you have available to you, right? It probably has more to do with the hardware of the computer that you're talking about. So if you've got an application where hardware, you want to keep the hardware simple, maybe because of cost, you're going to want a RISC, right? Whereas if money is no expense, like a supercomputer or something like that, then you might have more money to spend on hardware, so the CISC might be the way to go, okay? All right, so that's the end of that lecture notes. And again, at the end of every lecture notes, I give you a reading list, okay? So the ones that are grayed out were in previous lecture notes already. The one that is in bold is always the new reading assignment, so please be keeping up with that. It's not a lot of pages, okay? So it just fills in a little bit of the gaps. It's basically what we're talking about, but it fills in some of the details that we just don't have time to talk about in class, okay? So I highly encourage you to keep up with the reading list. It's basically what we're talking about here in lectures. All right, so let's move on then to lecture notes 4, where we're going to talk about branching and a very important topic called addressing modes. So again, we're going to be dealing with what I call generic assembly language. Okay, so we're going to be looking at some code. It's not code for any particular processor. It's sort of generic assembly language code that, you know, all we're focusing on are the different types of instructions. The actual syntax, like, you know, do you spell it this way, or do you put a pound sign here or that? Those kind of things are specific to a particular computer, which we're not going to, or a processor, which we're not really going to look at until we get into the ARM in a couple of lecture notes, okay? So we're looking at general code. So first topic is branching. In the previous lecture, I said very briefly that an assembly language program, any program really, is executed by the computer sequentially, right? The instructions that you write are stored in memory in order, and the processor starts at the first instruction, executes it, moves to the next instruction in memory, executes it, and so on and so forth, okay? So for instance, if we looked at some simple C++ code down here, where all we're doing is we're adding a number of numbers together, okay? That's all we're doing. And if we did this with straight line sequencing, you know, this is maybe the first, when you first learned programming back in 177 or wherever you learned programming, and you were asked to write code to add a number of numbers together, you might have done it simply something like this, right? Where, now we're using pointers here because these uppercase labels refer to memory addresses, okay? And so if num1 is an actual memory address somewhere in memory, they don't list it here, but, oh, down here. Okay, so this is memory with individual memory words. These are the addresses of those individual memory words, okay? Now, typically we deal with byte addressable memory, which means every byte in memory has a unique address. In this case, it looks like our memory words are 4 bytes long. So the address for the first word would be I. The address for the second word, which is 4 bytes later, would be I plus 4. Okay, because there's a unique address for every byte. And if a word has 4 bytes in it, then the address for a word would be I. The address for the next word would be I plus 4, 4 bytes later. Okay? So these are the addresses. So up here we have our actual program that's going to run to add these numbers together. Down here, these memory locations have been allocated to variables, if you want to call them that, where the numbers are actually stored in memory, the numbers that we're going to add together. Okay? So these labels represent memory addresses. So if we're going to use those in C++ code, we have to use them as pointers, which means we have to put an asterisk in front, meaning the contents of what num1 has in it. because num1 is an address. It's not a variable name, it's an actual address, okay? Okay, so that's why we're using pointers here, but the main point here is in straight line sequencing, if we're gonna add up a number of numbers together, well, we're gonna put the first number into a variable, call it R2, okay? And then we're just simply going to add the second variable to it, and then the third, and then the fourth, and fifth, all the way up to the nth, the last number. Okay, at that point, R2 will have the sum, and then we can write that back into a memory location, call it sum. Okay, so we have a number of instructions that get executed one after another. Okay, so this is basically a RISC type of processor, so it has a load store architecture, which means the first instruction up here, we have to load whatever is stored at memory location num1 into register R2. And register R2 is a register internal to the CPU. Okay, it's one of those general purpose registers inside the CPU that we can use. So this instruction is going to fetch the value of whatever number is here at the address num1, and it's going to put that value into the register R2. Okay, it loads a number from memory into a CPU register called R2. Okay, then the next instruction is going to load the next number stored at num2 into another register in the CPU called R3. Okay, so we have our first two operands in the CPU now. One is in register R2, the other is in register R3. The third instruction is going to add those two numbers together. It's going to add whatever's in R2 to whatever's in R3 and put the result in the first listed register R2. And that's a typical order in an add instruction where the last two are your operands and the first one is what we call the destination register. These are two, you add these two together and the destination for the sum is the first one listed, which is R2. So now R2 has the result of what was in R2 plus what's in R3. So we've added the first two numbers together. Okay, well now the next instruction, we have to go to memory and we got to get the third number to add to the result, okay? So it's another load. So we go to memory address num3 and we take whatever's number there and we put it into R3. Okay, it's the same R3 as we were used up here. We're done with num2, so we can overwrite it with num3. And then we just add it to R2 and put the result in R2. So we would just keep doing that. Load, add, load, add. Load always gets the next number from memory. Add adds it to our running sum. Okay, when we finally get to the last one, we've now got the total sum into R2. Now we want to store that back into memory at address sum. So we're going to store the results of R2 into the address sum. Okay? So that's a very typical assembly language type of program, in this case to add numbers together that are stored in memory. Any questions just about those basic instructions and what's going on? Okay, but it's pretty simple. Load goes to memory, gets a number, puts it into a register inside the CPU. Right? The CPU has to store it somewhere in order for it to operate on it. Goes to memory, gets the next one, adds it. Okay, load, add, load, add, load, add. Finally, when we got the result, we store it back into memory. Okay, well that'll work, right? Well, what's the problem with this? Anybody want to venture a guess? Why would we not want to do this? Sorry? It's inefficient because we're doing the same thing over and over and over, right? If you'll notice, this add instruction is exactly the same as this add instruction, is exactly the same as this one, this one, this one, this one, right? We write the same instruction over and over and over again, right? This, now these load instructions are all going to differ from each other because they're all loading from different memory addresses, but it's still the same instruction, right? We're loading something from memory, putting it in R3. Load something from memory, put it into R3, right? So we don't do that in C++ code, right? I mean, yeah, if it's just 3 or 4 numbers, you might do it. But as soon as it's more than that, you're going to write what? You're going to write a loop, right? Because if you have the same instructions or in C++, same statements over and over and over again, you put them into a loop. And you just keep going through that loop however many times you want, right? Well, we do the same thing in assembly language. So we need to have some sort of way of branching from just doing inline sequencing of instructions. We need some way of branching back so that we can implement a loop, okay? Back to this one, right? If we look at this add instruction here, the effective addresses of the operands, of the two numbers we're adding together, are registers, okay? The numbers are stored in registers. So we're using a particular address mode here called the register address mode. The effective addresses of our operands are registered, okay? That's pretty much all we've. All right, so we can do that, but we're going to slowly increase our vocabulary of assembly language instructions. Okay, we need a couple of additional instructions. Well, we're going to have to keep track of the number of numbers we've already added together somehow. We need to implement a counter, okay? That counter is going to have to decrement from, the total number of numbers down to 0 as we go through our loop. So we're going to use a subtract instruction or a decrement instruction to do that, okay? And again, this is just a generic assembly language instruction. This is not any particular processor. When we get to the ARM, you'll find out what the subtract instruction is for the ARM, okay? It's just a general processor. So something like this is how we could take whatever value is currently in register R2 and subtract 1 from it and put the result back into register R2. Okay? The pound sign here is a pretty universal symbol to refer to what we call an immediate operator, or pardon me, operand. Okay? It means this number 1 here, the actual number 1 would actually be encoded in this instruction. It's not stored in a register or in memory somewhere. It's actually part of the instruction, which means once that instruction has been written, this 1 never changes. It's always 1. Okay? Now, this particular application, that's okay. That's what we want it to be. So that's a subtract instruction. And we're going to need a branch instruction. We need some way of telling the processor, okay, once you get to this instruction, if a particular condition is true, instead of going to the next instruction in memory, right, branch back and go to a previous instruction. So that's what a branch instruction is going to do. And this is just, again, a very generic type of branch instruction that we're going to use to get used to all of these concepts. Branch if the contents, the square brackets always mean contents of. Branch if the contents of register R2 are greater than 0. 2, a memory address which is represented by the label loop. Okay, so that's what that instruction is going to do, just like it says. Branch if whatever is in R2 is greater than 0 to the memory address loop, okay? Obviously, if what's in R2 is not greater than 0, we don't branch, and the computer's just going to go to the next instruction stored in memory, okay, as you would expect. So in C++, it's basically like a for loop, right? That's exactly what we're doing. So, R3 is our counter. No, R3 is going to hold our running sum. And I guess R2 must have already been set. No, R2 is going to be set to 0, and it's going to increment it. No, it's going to decrement it. This should be, I think this is an error. This should be the value n, the total number, right? Well, then I'm going to have to change that too. This doesn't make sense. I think if we made this plus plus, right? Isn't that what we got to do? R2 starts at 0. Every time through the loop we increment it, and we're going to keep doing that until R2 hits n, the total number. Yeah, so that should be a plus plus. That's an error in the notes. Okay, so all we're going to do is you go into the loop, and there's going to be, this is a function, or this isn't even maybe real C++ code, some code that's going to update the address that we're going to read the next number from, and then we add it to our running total, and we keep looping through this for loop until we're done, right? And then this R3 is going to be stored in memory called sum. So that would be, C++ code, high-level language code that implements a loop. You're familiar with that. Okay, well, we can do the same thing in assembly language. So now we're going to need a counter to count. So that's going to be R3, okay? No, pardon me, R3 again is going to be our running sum. So one instruction is going to clear the value. If R3 had some number in it before, clear just means set it to 0, okay? We're going to load whatever is at memory location n, which is the number of numbers we're going to add up. Okay, so this load instruction is going to take the value n and put it into R2. So R2 is our counter. Okay. So I don't think this code actually matches this code. This for loop is kind of screwed up. So we're going to start with that many numbers to add up. We're going to clear register R3. It's going to hold our running sum. And then we're going to have some code here, which we'll look at in a minute, which simply determines the address of the next number, and then some code that loads that next number into a register R5. And then we add the contents of R5 to R3 and put the result back in R3. Okay? We're going to subtract 1 from our counter. So R2 had small n in it, the total number of numbers. We subtract 1 from that. And then we branch if R2 is greater than 0, meaning that if we haven't gotten to the last number yet, we branch back to this memory address loop, which is up here, where we determine the address of the next number to be added in memory. Okay? We load it into the same register R5, and we add it to our running sum that's contained in register R3. And we're just going to keep, then we decrement the value of R2, that's in R2 again, branch. We're just going to keep looping here until we finally have got to the last number, in which case this will be false. And then we just go down here to the next, and we store the result, which is in R3, into the memory location sum. Okay, so now we got a lot fewer instructions. We've just got a few instructions here that we are going to loop through to add the numbers. So it's just like in high-level code. Okay, so those are branching instructions. Any questions about what we did there? And we'll look at exactly how to do that in a minute. Yep.
It's more of a syntax question than anything. Just in terms of the greater than 0, is there in the assembly language something for like null values so that if you had 0 as an actual number in one of the registers?
Yeah, we can check for that too. Yeah, how these branch instructions are actually executed is with what we call condition codes. And one of the condition codes is 0. So if a particular instruction results in a value of 0, no matter what that instruction's doing, then the next instruction can be a branch instruction that looks at that condition code, which is a bit in a certain register in the CPU. If it's a 0 or a 1, it tells it whether the result was a 0, which is then how it will decide whether to branch or not. Yeah. We'll look at that in a little bit. Any other questions? Yes, sir.
Is there a reason why in assembly code language we decrement instead of incrementing and then stopping the loop?
Not really. You can do it the other way around. You can set it to 0 and check, well.
If you only continue the loop as long as R2 is...
It's a little easier to do this way. No, I shouldn't say that. Because you could also increment it and check if it's less than n, right? But encoding that branch statement with n instead of 0, it makes a little, once you look at how those branch statements are actually executed or implemented, it makes a little more sense to do it this way, but you could do it the other way. Okay. For instance, let's go that so far. So condition codes, as I said, there is a register. It's usually called the status register in a CPU. And again, a register is just a special memory location that's on the same silicon chip as the processor itself. So it's very close to the processor. It's not in the main memory unit, okay? So there's another register, and it's usually called the status register. So it has individual bits, and some of those bits are reserved for what we call the condition codes. And these condition codes are set and reset by arithmetic and logic operations. So whenever the arithmetic and logic unit, the ALU in the CPU, adds two numbers together, or it ANDs two numbers together, or ORs two numbers together, these condition codes, the processor looks at the result of that operation and sets, or resets these condition codes appropriately. Okay, so there's four main ones. There's negative, or N, which basically says if the result, the previous instruction that the ALU just did, if that result resulted in a negative number, well then that bit, that N bit in the status register is going to be set to a 1. So now you as a programmer, if you've just, I don't know, subtracted two numbers together, and what you do next in your program depends on whether the result was positive or negative, well then the next instruction you're going to do is you're going to check what the value of that N bit is in the status register. If it's a 1, you know that the previous instruction resulted in a negative number and then you do something. If it's a 0, you know the previous value that was just calculated was a positive number, you're going to do something else. You've got a 0 bit, okay, which is very important for, pardon me, the branching instructions. It's used by a lot of branching instructions. And again, if the previous instruction resulted in a 0, this bit will be set to 1. If it didn't, it'll be set to 0. Overflow and carry we've talked about already. So if the previous instruction was adding two numbers together and the result of that addition is bigger than the number of bits that you have to store it in can hold, that's what we call an overflow. So if that happens, the processor is going to set that bit to 1. A carry, if you add two numbers together, even if the result does fit within the within the number of bits in a word, but if a 1 was carried out of the most significant bit, right, if we're dealing with 2's complement, you can ignore it, but the processor will still set this to 1 because maybe you're interested in that for some reason, and you as a programmer need to know when that happens. So you can always check that bit in what we call the status register. Okay, the N and Z bits can also be affected by move, load, and store. Load instructions are go to a memory address, get the number that's there, and load it into a register in the CPU. Store is take a number that's in a CPU register and store it in memory somewhere. Move are a little bit more flexible instructions. A move instruction, you can move two numbers between two different registers. Or in some machines, you can move a number between two different memory locations. Or you can move a number from a memory location to a register or vice versa, okay? So, and these are typically more in CISC type of machines, but sometimes you see it in others as well, okay? But if I, for instance, load a number from memory into a register in the CPU and that number happened to be 0, well then the Z bit, the 0 bit, will be set by the processor, indicating that what you just moved or loaded from memory was actually a 0, which is obviously handy sometimes too if you want to know that, okay? So these are what we call the condition codes. There's a lot of other ways to do it. All right, and so we'll get into that a little bit more when we actually look at more of the branch instructions and how they're implemented. Okay, so we're just sort of, we're covering a lot of different type of topics just so that you got the basics. Okay, so the main part of this lecture though is what we call addressing modes. And this is kind of the hardest thing to sort of wrap your head around. But once you got this, then it's sort of the crux of the mountain, if you want to call it that, okay? So once you got this, the rest is gonna be pretty simple. So the whole thing about addressing modes is, and you've probably already seen or seeing this when, where's my clock go? There was a clock on here. Don't let me go over time, I forgot my watch today. All the instructions we're dealing with, pretty much, most of them, we're obviously dealing with numbers, okay? Those numbers have to be stored somewhere in the computer. They're just not out in free space somewhere, right? They're either stored in a memory location or they're stored in a register in the CPU. How we reference a number in any location in a computer is what we mean by addressing modes. And there's lots of different ways to do that. We've only looked at very simple ones so far. We've basically really only looked at what we call the register addressing mode, okay? Which means that the place where our number is stored, or what we call the effective address, okay? The address of where that number is stored is a register, okay? So, just going back here. Okay, and this table is a little bit of an expanded version of the table that you'll find in your textbook in Chapter 2. I highly suggest you look at it every once in a while and just sort of practice remembering what these different addresses mode, because to be honest, this is really the hard part of reading or writing ARM code, right? On the midterm, I'm probably going to give you a small section of ARM code and ask you, you know, what's in register R5 when these 10 instructions have executed, okay? The hard part, how do I make it hard? I use different addressing modes. That's really all I can do, okay? So if you can figure out, remember what these different addressing modes are, it's no sweat, okay? Then it's just you recognize the instructions. Oh, okay, I'm getting the number from here, I'm adding it to this one. Okay, well, what's the address for this number? Well, I'm using this mode, so it's this, et cetera, okay? That's really all there is to it. So we're gonna be looking at a bunch of these. In your book, it only shows up to here, I think. It only shows this section, because these are basically addressing modes that you see in most RISC machines, whereas these last three, I should say the last two. This one is probably part of RISC too, but the last two here are typically only found in CISC machines. Although the ARM, which is basically RISC, also includes these, so I can't say that it's always true. Okay, yes, sir.
Sorry, just regarding what you just said about questions like this one, the final, so we should memorize all of this stuff?
You have to know these addressing modes, absolutely, yep. You gotta know these addressing modes, otherwise it's impossible to read a little bit of ARM code and know what's going on. And so that's why I say, you know, that table in your textbook, it's probably table 2.1 or something like that. Okay, is that what it is? Anybody got it? Okay, thank you. And it's basically, I think it's just these top, I don't think it includes the last two. It's just these, yeah. Hopefully by the midterm, you can picture that in your mind and you know what they all are, okay? That's the goal. Okay, we're gonna be looking at these one at a time. So the key here is determining for a particular address mode, what is the effective address of the operand that's being referenced, okay? The effective address is where is that number stored? Is it stored in a memory location, and if so, what memory location? Is it stored in a register, okay? And so the assembler syntax, you know, this is what most instruction sets that use these address modes, they'll use some form of this syntax in your actual assembly language instructions. And this here tells you what the effective address is. Okay, so in the register mode, which we've been dealing with already, you know, that add R2 to R3 and put it back into R2, the effective address is a register. So that's where the number lives, inside of that register, okay? Okay, so let's look at some of these. So like I said, the register mode, addressing mode is probably the most straightforward and easiest to understand, right? The operand is the contents of a processor register, okay? So the syntax is simple, you just list the register. I could be, you know, a lot of, I forget exactly how many registers in the ARM. I want to say 16, but it's somewhere around 12 or 16. Okay, so this I will be 12 to 16, 1 to 16, for instance, if we're talking about an ARM processor. There's only a certain number of registers that you have available to you. So the effective address is the register. So like this example we had, right? Adding what's in register 1 to what's in register R2 and putting it back into R1. We're using the register mode, so that's pretty straightforward. Okay, well maybe the number we're needing is actually in memory, in which case we use what's called the absolute or the direct addressing mode, okay? Absolute meaning we're using an absolute memory address as the effective address, okay? So the syntax is we've got some sort of, it could be a number, you know, and if we use a memory address, it's typically written in hex, so we put 0x in, and you know, you might have some sort of memory address like this. You know, it could be that, or typically it's a label, and we'll talk about how that label is defined later on, but typically it's a label that represents a particular address in the main memory unit, okay? So the effective address is simply the address in memory, and so an example would be this. This is a move instruction, which in some processors can be used like a load instruction or a store instruction. So it could be move the contents of the memory address LOC and put it into register R2, okay? So this is a little bit of a mix because we're using a register and a memory address, okay? Which is often, in some processors, what a move instruction does. Yes, sir?
Is it move like different at all than a load? Like, is it write just like behind it, like the memory? Like,
Does it what?
does it write the, are you literally moving the number? Like, do you leave anything behind?
Oh, you do, yeah, in all of these, you never, when you transfer a number from one place to another place, we call where it was the source and where it goes the destination. And pretty much any instruction, the source stays the same. You just make a copy of it and put the copy where you're going.
Yeah, so there's like between move and load.
Yeah, it depends on the processor. And some processors will only have load and store. Some processors will allow you to use a move to get a number from memory. It all depends on the processor, okay? So some will have some won't have move at all. Most do, but you can only move between registers, for instance. Some processors, their instruction architecture will allow you to move between a register and a memory address, okay? So remember, we're keeping it general, so. Okay, and again, once we get to the ARM does have a move, and we'll look at how it works for the ARM in particular, okay? Okay, so that's the first two. The third one is what we call the immediate, okay? And immediate means whatever we're dealing with is right there in the instruction along with the rest of the instruction, okay? So typically we use a pound symbol, right, a hashtag, in front of the actual either number or address, okay? Now in this case it's being used as a number, right? And that's how we typically use the immediate. The number that we want to subtract from some other number is what we call the immediate operand, so that there is no effective address, while the effective address are the bits inside the instruction that actually hold this number, okay? So in this case, the actual operand is 200, and so we would use it something like this, right? This subtract instruction is going to take the immediate operand, the number 200, subtract it from whatever's in R3 and put the result back in R3, okay? So in C++ or any high-level language, does this remind you of a particular type of variable? Well, when you write this instruction, put it in an assembler language program, does the 200 change ever? No, once it's encoded in that instruction, it's, sorry?
Is it a global variable?
Say that again?
Is it a global variable?
No.
Once it's at 200, it's like, it's not set anywhere, it's like.
It's actually part of the instruction. So if it can't ever change, what do we call that in C++? A constant, right? This is like a constant. It never changes. Once you've written the code, it's always 200 that's subtracted from R3. Right? The user can't change it, the program can't even change it. So it's like a constant variable in a high-level programming language. Somebody mentioned a global. Pardon me. This is like a global variable. Okay? Pardon me. Because an address in memory could be accessed by any instruction in my assembler language program, right? If I know where that number is, if I know that label LOC, I could write any instruction in my assembly language program to go and get the number that's there. It's like a global variable in a high-level program language, okay? So this is like a global variable. This is like a constant variable, if that helps you. If not, don't worry about it. It's not critical. Yeah?
So that 200, it doesn't have to be defined anywhere. It's like in C++ where you can subtract 200 and the compiler will know what 200 is. Like does that mean that the processor, like nowhere there needs to be like, no one needs to set like the binary number of 200 somewhere aside to be able to use it?
This binary number 200 will be in the actual ones and zeros that this instruction is made up of.
So it's still in the instructions.
It's in the instruction, right? So when you implement a constant in C++, I'm not sure, so I'm not even gonna go there. But,
Okay.
so I'm just gonna answer your question and not add to the confusion. Okay? Because remember, these instructions, like in a RISC computer, like in the ARM, this instruction is stored in 32 bits in memory, right? Part of those 32 bits is a code that specifies that it's an add instruction. Some of those bits will specify that it's R1. The sum will specify that the second register is R1. Another set of bits will specify the register R2. And in this one, another set of bits will hold the actual binary number 200. Okay? So that's what we mean by immediate. So those three are pretty simple and straightforward, right? Register, effective address is a register. The operand is whatever's in that register. Absolute or direct, the effective address is a memory location in the main memory of the computer. The effective address is that. The operand is whatever's stored at that main memory address, okay? And immediate, the operand is an actual number that's inside the instruction itself, and therefore it can never change. It's always 200, okay? And we specify by the pound symbol. Okay, so those are the first three basic ones. Now the indirect mode is a little bit more complicated, and if you hated pointers in 177, I apologize. You're going to have to figure out what a pointer is again. What was a pointer in 177? It was a variable that ever only could hold what? Anybody remember?
The address.
An address, right? A pointer in C++ is a variable that can only hold an address, right? And so we use pointers in C++ to do basically what we call indirect addressing. Is it already 1:45? Wow, time goes by fast. These 50-minute lectures are so short. Okay. So let's just focus on the RISC style here. The CISC is similar. Let's just focus on the first one here, okay? So the syntax is parentheses. So when you put parentheses around a register, for instance, inside of an instruction, that means the effective address in this addressing mode, in the indirect mode, is the contents of what register RI holds, okay? The effective address, not the operand, not the number itself, but where the number is stored inside that register. So what does register R hold? Holds an address. It's like a pointer, right? A pointer is something that holds an address. In the indirect mode, a register is going to hold an address. Okay, so the effective address in our symbol, in our notation here, is equal to the contents. The square brackets means contents of register RI is the address of where my operand is stored. So for instance, in something like here we've got a load instruction. Load means go to memory, get a number, and put it into the CPU, in a register in the CPU. Okay, so where are we putting it? We're putting it into R2. Where is the number? Well, the number is at an address, and that address is stored in register R5. So here, if this is our main memory, and this is our CPU, oh, pardon me. It jumps around like that. Okay, this is our CPU over here. Our general purpose register R5 is inside the CPU. And here we got our main memory on the left-hand side, okay? Well, if our register R5 holds a label B, for instance, which refers to a particular address in our main memory right down here, well then the number we're going to load from memory is at address B, okay? This is our instruction stored in memory as well, okay? We're gonna load whatever number is stored at the address that is currently inside of R5. R5 contains this address, B. Okay, it's really a sequence of zeros and ones that refer to a particular address in memory here. Okay, so this load instruction is going to go to this address B that's stored in R5, get the number that's stored there, and put it into register R2. So somewhere here in the CPU is also R2, and our operand gets put into there. Okay, now in the next instruction, we're going to combine that number with some other number, presumably. Yes, sir?
You also have, specific, say you had specific add functions or subtract functions within a register. Like, can you store anything but a number or value to be in the register?
can I store anything but a number or value in a register? Is that what you asked?
Yeah, essentially, so.
No,
Yeah.
it's just numbers and addresses. Yeah. And, well, you can store an instruction in in a register, because remember, somewhere in the CPU, we also have what's called the instruction register, which takes the ones and zeros from this instruction and puts it in there so that the CPU can decode it and figure out what to do with it. But again, that instruction is just a sequence of ones and zeros, right? So the ones and zeros in a register, it could be an instruction, it could be a actual number that we're adding or subtracting, or it could be a memory address, okay? I think that's about all you can do. That's about all there is. Okay, I'm sensing that we're done. Yeah, I think we're done, right? You bet. Okay, we'll see you on Friday. We'll look through this one next